You ever look at your Wi-Fi router and just kind of wonder, what's the deal with all those antennas? I mean, does it really need to look like some kind of strange sci-fi insect? Well, I can tell you it's definitely not just for show. In fact, it's a sign of some truly brilliant engineering at work designed to solve a huge, fundamental problem that affects pretty much everything that's wireless. And the secret behind all that hardware, the magic that keeps your connection from constantly dropping out, is a concept called wireless diversity. So, in this explainer, we're going to pull back the curtain. We'll break down exactly what that means and how it's become the invisible foundation for our super connected world. So, here's our game plan. First, we're going to look at the core problem, the fickle, unpredictable nature of wireless signals. Then, we'll dive into the elegantly simple strategy engineers came up with to solve it. After that, we'll see how both our devices and the things sending them signals use this strategy. And finally, we'll look at where you can see this amazing tech in your everyday life. All right, so first things first, before we can really appreciate the solution, we've got to understand the problem. And believe me, when it comes to wireless signals, there's a big invisible villain that's constantly trying to sabotage your connection. And this villain has a name: multipath fading. It sounds technical, but the idea is actually pretty simple once you picture it. See, when your router sends out a radio wave, it doesn't just travel in one clean, straight line to your laptop. No way. It's more like a splash. The signal radiates outwards and starts bouncing off of, well, everything. The walls, the ceiling, your desk, even you. So what your device actually gets isn't one clean signal, but dozens of copies or reflections that all arrive at slightly different times. And sometimes those copies clash. The best way to picture this is to think about ripples in a pond. You know how that works, right? Drop one pebble in and you get these perfect, clean waves. But what happens if you drop 2 pebbles in? Well, it gets messy. Where the peaks of 2 waves meet, they join up and make an even bigger wave. That's great. That's a strong signal. But where the peak of one wave meets the trough, the low part of another wave, they completely cancel each other out. You got a little spot of flat water. That is exactly what happens with radio waves. And when they cancel out, you get what engineers call a deep fade, a tiny invisible dead spot where the signal strength plummets and for a split second nearly vanishes. And that's what causes your video to buffer or your call to get choppy. So this multipath fading sounds like a huge pain, right? How in the world do you fight against an invisible dead spot that's constantly moving and changing as you walk around? Well, the solution is surprisingly simple. And it's just beautiful in its logic. If any single path can be unreliable, why not just use many paths? And this is where the pure genius of diversity comes in. This quote from the textbook Wireless Communications by Goldsmith just nails it. The whole idea is to create multiple independent paths for the signal. You're basically playing a numbers game. If you only have one signal path and that path happens to hit a deep fade, well, you're out of luck. Your connection is gone. But what if you have 2 paths, or 4? What are the odds that all 4 of those paths are in a deep fade at the exact same millisecond in the exact same spot? The chances become incredibly, incredibly low. You're essentially guaranteeing that at least one good path is available at any given moment. Okay, so this many path strategy is great in theory, but how do we actually do it in the real world? The most common way is to put the smarts on the receiving end. That means your phone, your laptop, your smart TV. We call this receiver diversity, and it's where your device actively fights back against fading using a few really clever tricks. The simplest trick in the book is something called selection combining. It's a really straightforward process. Step 1. Your device is constantly listening. It has multiple antennas, and it's always measuring the quality of the signal coming into each one. It's looking for the best signal-to-noise ratio, or SNR. You can just think of SNR as signal clarity. Is the voice you want to hear loud and clear, or is it getting drowned out by background static? Step 2. After checking all the paths, the device simply picks the winner. It selects the one single antenna that has the cleanest, strongest signal. And step 3, it uses only that path, but it never stops monitoring. The microsecond that another antenna starts getting a better signal, bam, it seamlessly switches over. You never even feel it happen. Now, just picking the best signal is a fantastic start. That's selection combining. It's simple, it's low on power consumption, and it works pretty well. But engineers always want more performance, right? So they developed smarter methods. There's equal gain combining, which takes the signals from all the antennas, carefully lines them up so they add together constructively, and combines them. This gives you an even better, more robust signal. And then there's the gold standard, maximal ratio combining. This is the smartest of all. It not only combines all the signals, but it intelligently gives more weight to the stronger ones. The result is the best possible signal you can get. But here's the catch. It's a classic engineering trade-off. As you go from good to excellent to optimal, the complexity and the processing power needed go way, way up. So the choice of which method to use always depends on the device and what it needs to do. So putting multiple antennas on the receiver is a fantastic strategy. But what if we flip the script? What if your phone only has one tiny antenna, but your Wi-Fi router has 4 big ones? Can we put the smarts on the transmitting side instead? You bet we can. And this is where things get really fascinating. This introduces a whole new puzzle, though. Think about it. A receiver can just sit there and listen, measuring which of its antennas is getting the best signal. But a transmitter, well, it's just shouting into the void. It's sending signals out. It has no idea which of its antennas has the best path to your device at any given moment. It's essentially flying blind. So how on earth can it provide diversity if it doesn't know which path is the good one? The answer is one of the most ingenious solutions in all of modern communications. It's called the Alamoudi scheme, and it is pure mathematical magic. Instead of trying to guess the best path, it uses a mind-bending trick that involves both space, the different antennas, and time. Basically, the transmitter encodes the data in a very special way and sends different parts of that encoded signal from its 2 antennas over 2 separate, very brief moments in time. To the receiver, this might look like a jumbled mess, but because of that special encoding, even a simple receiver with just 1 antenna can use some elegant math to perfectly unscramble the 2 signals and treat them as if they arrived on 2 completely independent paths. It literally creates diversity out of thin air. Just an absolutely brilliant piece of engineering. Okay, so we've waded through some pretty deep technical concepts, from combining ratios to space-time coding. You might be thinking, this is really cool, but why does this matter to me? Well, it matters because this technology, this whole concept of diversity, is the invisible engine that powers our entire modern connected world. Seriously, this tech is everywhere you look. Those antennas on your Wi-Fi router are part of a system called MIMO. That's multiple input, multiple output, which uses these exact principles for stronger, faster internet. Your 4G and 5G cellular connection, it's constantly using diversity between your phone and the cell tower to stop calls from dropping and keep your data speeds high. Even the Bluetooth connection between your phone and your headphones uses a form of diversity to keep the music playing smoothly, even when your phone is in your pocket. It's the fundamental technology that makes our wireless world reliable enough to actually use. So there you have it. That's the secret behind all those antennas. It's all about playing the odds, using clever math, and multiple paths to beat the fickle nature of physics and give us the stable connections we rely on every single day. If you enjoyed this breakdown and learned something new, please do us a huge favor and subscribe to the channel, like this video, and leave a comment down below. Ask us a question, or let us know what other tech topics you'd like to see us dive into next. Thanks so much for watching.